Hello.
Hello, Professor. Happy New Year.
Thank you, brother. Same to you. Abhiyan.
Professor, how are you?
Doing good, doing good. Yeah. You have your name written in Hindi.
Yeah, in Nepali actually. I'm trying to
I've-
rename this. Yeah, I just.
No, that's good. That's good. So, yeah, at least it seems like it's very similar to Hindi. Yeah. So Nepali.
Yeah, this alphabet is like same.
Okay. Okay. Oh, now you changed it.
Yeah, I was trying to change.
Yeah. Nice. Okay. So let's see. Let me nice to see you.
Yeah, nice to see you, Professor.
Okay, we have one more person. Ken also needs to be here, right?
Okay. But
Okay.
this time also, three of us in this dynamics, or are there any other?
Apparently only three. I mean, last time when I checked about 3 days back, probably 2 or 3 days back, and there were 3 people enrolled, and it was you three, Ken, you, and Hriday. Yeah. So maybe someone else has joined since then. I don't know. So yeah. So let's
And
wait.
how was your tour to Dubai, Professor?
Oh yeah, it
Oh, you
went
went to
smoothly.
Dubai?
Yes, I went to Dubai. I was planning to go to India, but it never worked out. I had to cancel that because of all the uncertainties related to COVID. But my parents were in Dubai.
Oh,
Oh yeah, that's nice thing. You met your parents, I think.
Yeah. So my sister pretty much lives. She has been there for quite some time, and so it worked out fine. But in the last 2 days, like I tested negative, so that's good. But my wife had some like what is it, cough or running nose, basically, not even cough. So we tested, both of us tested, so it is both negative. So it seems okay, but I'm not coming to the department just to be safe. So this is actually a house, not department. So hopefully this comes out clear.
Yeah, this is clear. You have a big blackboard in your house.
Yeah. So yesterday there were some complaints from undergraduate introductory physics students saying that this was not clear. But today I taught classical mechanics to graduate level students. So they said and it seems like it was perfectly fine. The only difference was I closed the window. So it's slightly counterintuitive that if you close the window, it's better. So I think the contrast comes out better, I guess. Yeah. Okay, yeah.
Can you
how are
see me,
you?
Professor, or is it?
Yeah, go ahead.
Can you see my face? I mean, I'm not
sure.
No,
I see black box for that. And Ken, for a moment, I could see him, but then he chose to switch off the camera, I guess. Yeah.
Yeah, maybe I need to change my settings.
Yeah. Ken, are you speaking? I think you unmuted yourself, but I cannot hear you, Ken.
Yeah, I just unmuted myself, but yeah. Can you hear me now?
Yes.
Okay, great.
Good, yeah. If you feel comfortable, feel free to put on the camera, but that's not a requirement.
Oh, okay. I couldn't see I couldn't see anyone else's camera on, so I just turned it off. But
Oh, okay. No, Abhiyan has camera on. I think you should see him.
Oh.
Yeah.
No, I can't see anything, honestly.
Really? Yeah. Again, hopefully this is just 2-3 days, 2 lectures. So don't sweat on it. Oh, nice. You have a nice background, Ken. Oh, we lost you.
Yeah.
I think it was Moses also has pretty much the same background as you. Yeah.
Oh, really? Well, yeah.
Yeah, interesting. Okay.
So
Okay.
I'm actually gonna leave and come back because I can't see any like of anyone else's camera. So I'm just gonna see if that fixes it.
Me too.
Okay, do that. So, Bhiyan, did you go anywhere? Probably not, right? You said you're not planning to.
Me, Professor?
Yeah.
Yeah, I went to Florida.
Okay.
I visited there. There are some friends. I met them.
Okay.
I was
okay.
there for 4 days.
Good. Good. Did you fly or?
Yeah, this route is too long. I went to Chicago, and from Chicago I fly.
Okay. Did you use the train or?
Yeah, from Carbondale to Chicago I use train.
Okay.
It is hard to get direct flight from Carbondale to.
Oh yeah. Yeah, not a easy thing. Yeah. And the train prices have increased, I noticed this time when I was traveling. Earlier it was cheaper.
I don't know it's cheap or like expensive. It costs 78 for one round, not single way, one way for two.
For two people, right?
Yeah,
Yeah, that seems
I think it's
reasonable.
cheaper or like.
Yeah. Earlier it was a little cheaper, yeah. Okay, let's see. So now we have two Kens.
Yeah.
Is that two devices or is it just the other one doesn't go away?
I don't know why. Yeah, it should. One of them should go away.
Sometimes it automatically splits like.
I see. Hriday, we still don't see you.
Yeah, I didn't find
Okay.
the setting.
Yeah, don't. Let's not sweat on it. Take time. Okay. As far as the procedure for the course goes, I don't have to really go through it because all three of you have taken a course with me. We will use exactly the same process: 2 midterms, homework, and quizzes are the same as usual, except that I don't expect to give quizzes every lecture, but otherwise pretty much the same as earlier. Okay. Any questions on that? So I don't have to go through the syllabus then. Yeah, Hriday?
For syllabus, I think it's okay. You don't need to go over it.
Yeah.
Again.
And if you go to the website, do you know how to reach the website for the course?
Yeah, I know.
Yes.
So if you go to my page and then there is a link that I created for this course, you should be able to reach there. Currently, of course, there is not much there. Hopefully but there are links to last spring courses, which is nice because of the pandemic. There were a lot of recordings, so you have experienced that last semester also. So you should be able to access that. Okay. Now, so here is a confusion I have. It was hard for me to decide what to teach because I really don't know what you have covered in the first semester. I should have talked to Dr. Lee, but I not reached the department yet. So can you guys fill me in there? So what all did you cover in your first semester? Do you think you guys can help me in that?
I think the first semester we mostly focused on first 4 chapters, 4 or 3 chapters of quantum mechanics, David Griffith.
Not quantum mechanics, right? You mean?
No, sorry, electrodynamics, my bad.
Yeah. And first 3 chapters. So let's see if I have a book here. Give me a second.
Yes, sure thing.
So I assume you systematically went from one section to the other. So let's see. First 4 chapters, you say, right? So electrostatic potentials. Oh, okay. Oh, that's good. Okay. So you guys finished electrostatics pretty much, and I can do magnetostatics then.
I believe we also covered a good majority of magnetostatics as well.
Okay. Okay. So that means you went chapter 5 also. That's nice. Okay.
I think if in magnetostatics, he mostly taught us basic stuff, not that in depth, I think. I
Okay.
think, but I'm not sure.
Did you? Okay. That doesn't help much. That comment doesn't help me sufficiently. Okay.
What's the video?
I do remember a comment that you would like to see Green's function more, right? I think it was Ken Yu who said you would like to see Green's function more. Okay. And is it correct? I mean, so if I repeat the question, you have done magnetostatics a good bit.
Yeah,
Like you have covered what's the magnetic field due to a
yeah,
let's say
magnetic field intensity we have studied, and
okay.
something about dipoles as well.
Magnetic dipoles, you mean,
Yeah,
correct?
yeah.
Okay, okay, that's reasonable.
Yeah, I think the very last thing we did was chapter 6 from my notes.
Oh, okay.
From last
So that
semester.
means you really did chapter 5. That's good. That's good. Okay. So
Yeah, the very last thing we talked about was the phase transition, and we didn't really talk about it in depth.
We studied up to chapter 6, magnetism.
got it. Yeah. That's a good bit. Yeah. I usually cannot cover that much. That's good. Okay. So what I suggest is and you're using Griffith's book, right? Yeah. So okay. So I propose that we do, let's say, surely chapter, related to chapter 8. I will not go section to section in Griffiths, but the concepts related to chapter 8, these are broadly called conservation principles. Yeah. We'll begin with this. Can you read this, by the way?
Yeah, conservation principle.
Oh, maybe I should zoom in. Let's see. Yeah, it's not a
Yes, now it's better.
okay. Yeah, not a significant zoom, but that's the best I can do. Okay. Okay, and so chapter 8. So this is basically when we talk about electromagnetism. What is the conservation of energy, momentum? In fact, we will also try angular momentum and so on. So that's what is covered in chapter 8 in Griffith, and then we will do we would like to do electromagnetism or electrodynamics in the sense when electric and magnetic field is there together, right? But in between, I will come and do Green's functions. So this is anyway necessary because we need Green's function to do the next part. So let's say this is not related to any chapter in Griffiths, right? So we just put a dash here, and then we do electrodynamics, right? So this is electrodynamics. Which is basically chapter 9, 10, and yeah, chapter 9 and 10, let's say. This is chapter 9, 10. And then this is closely related to what we call radiation. Radiation is a specific solution of electrodynamics in the sense that we are interested in far regions, like let's call it far field approximation. And this is chapter, I see, chapter 11. And somewhere in between, actually, I will do relativity before, right? Right after 10, you can also do relativity, probably. I like to do chapter 12 before chapter 11. So this is special relativity. In the electrodynamics context. Okay, so yeah, that could be a strategy how we can proceed. Okay, is there anything else you guys would like to see in this course, which I can try? I cannot promise. Something that you think you expect to see in electrodynamics?
Okay, to be honest, Professor, from the last class, if I not right now, I'm not sure. If I feel like I want to go over some topic again, I will let you know later.
From the last semester, you mean?
Yeah. I mean,
Sure.
if I feel like.
Yeah. If you guys want me to go over something, that's also possible. So just let me know.
Yeah, thank you, Professor.
So I will assume that you've seen a good bit of electrostatics and magnetostatics that is completely separated, like electrostatics on its own and magnetostatics on its own. And here what we are doing is we are going to mix up the two. Okay, so now there won't be any distinction between electric and magnetic field. There's another question that comes up. We always talk about units in introductory physics courses. Everyone likes to use their own units. A classic example is where in United States, we keep using miles and gallons and so on, which is okay. As far as we know the conversion, right? We should be able to convert from one to the other. But this is a relatively easier conversion. We just have to change the numbers, correct? Your equations don't change, right? Like for example, if you're writing Newton's laws, F equal to mg, or better, let's say density, right? Density is mass per unit volume. So your equation would be rho is equal to m over v. Right? Like if I say m is mass, v is volume, this equation doesn't change whichever units I use, correct? Like whether when I'm writing this equation, I don't have to tell you I'm using SI units or 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 CGS units or so on, like whether I'm using centimeters or meters, it doesn't matter. But unfortunately, in electrodynamics, that's not the case. Equations change forms, or there are some expressions that there is a tiny change in the expressions based on which units you work with. Okay. And that raises the question as to what are the units we would like to use, and what are the units that was used in your first semester. From what I understand, you've used Griffiths, so Griffith uses SI units. Okay, but most of the textbooks, somewhere in between, halfway down the line, they change units. Okay, just because when it comes to electrodynamics, it is easier to use what is called CGS system, or more broadly called Gaussian units. Are you familiar with this? Okay. Okay, if you're not familiar, that's your first homework, because I wanted to give a first homework. I did not know what exactly I will be teaching today. So I gave this problem, which basically connects different equations in different units. And you will see that there is a significant difference between the equations. I will use SI units, and it is nice that you guys used SI units in the earlier semester. So that shouldn't be a challenge at all. But you should be aware that units, in different units, equations look different. So let me write down. So what are our equations? Right? Let's write down the Maxwell's equations to begin with. So just so everything in this course revolves around Maxwell's equation. No, that's hopefully you have seen that sufficiently. So let's write down Maxwell's equation to begin with. And how many Maxwell's equations?
4.
4, right? Good. So what's the first one, or any one of them? Tell me one Maxwell's equation.
Gauss law.
Gauss's law, good. And what does it state? So let's call it Gauss's law. Is it readable, by the way?
Yeah, it's perfect, I think.
Okay, good. So what is Gauss's law?
I think flux going perpendicular to area is equal to the charge enclosed by this closed surface.
Mathematically, how do you say? Yeah, that's correct statement. Good.
I think line integral of closed integral of E dot dA equal to Q by E0.
That's correct. Let me write that here. So not line integral, surface integral.
Oh, sorry, E dot dA.
Of dA, that the area dotted with the electric field, is equal to the charge enclosed. Right. Q enclosed, let's say. Right. Am I missing anything?
Epsilon naught.
Yeah, epsilon naught, right? So there's an epsilon naught in here. That's an integral form of the Maxwell's equation.
Yeah.
What's the differential form?
Del dot E equal to rho by E0.
Perfect. Okay, del dotted with the E. So I will write this as D. Okay, is equal to rho, right? Where rho is charge density, charge per unit volume. And I've introduced a D here. So let me define that. D is going to be equal to epsilon naught. And it is nice to see it like this, because if there is a medium, then there is an epsilon, even though it comes with significant amount of complications in the sense you have to have frequency dependence and all. So all this is in the frequency space instead of time space. So, so that's or yeah, let me avoid those, because now we have done electrostatics, done magnetostatics, all the material medium is over. Now we are mostly going to be working in vacuum. So why worry about it? Typically I stress on this, but now I think we are in the second semester, right? Second semester is relatively easier. So I'm saying easier as far as construction goes. So let me write this in this form. And then I can actually stress on the fact that this is a position and time dependent quantity. Earlier, I couldn't have done that because then I'd write it in the frequency space. But let's not worry about that. This is a position and time dependent quantity, and this is charge is rho and t. Okay. And let me get a look. So it's the same thing, but we will mostly use a differential form, but the content is the same in the two things. Okay. Clearly, there are two things. There is a charge density. So let's say there is a point charge. So there is one charge sitting there. It creates an electric field. Right? Notice that electric field is not localized. A charge is a localized concept in the sense that it has a volume. A charge, when you think of an electron or a proton, you think of it as something having a volume. It's probably spherical in shape, like for a proton, we expect it to be spherical, but maybe not, right? And electron similarly has a volume. It occupies a very small volume. But the electric field, on the other hand, is not a localized concept, right? When you say the electric field of a point charge, it goes all the way to infinite, right? So it is a field. That is what we mean by a field. So this is a concept where it is everywhere in space and time, if you want. So that's electric field, and that's a charge. And what Maxwell's equation is talking about is that we give this is given, and we are asking what is the electric field. I can ask the opposite question also. If the electric field is there, what happens to the charge? Correct? So there are two quantities in here. There is electric field and there is charge. If there is an electric field, it will move a charge. If there is a charge, it will create an electric field. And the dynamics between the two is what we are interested in. But what Maxwell's equation tells us is, it doesn't tell us what electric field does to a charge. What it does is, what the charge does to the electric field. Given a charge, it creates an electric field. That's what Maxwell's equation does. Maxwell's equation doesn't tell me what happens to the charge if there is an electric field. What Maxwell's equation does is, if I have a charge, what's the electric field created by that charge? Is that reasonable? Clear? Any questions there? Okay, so that's Gauss's law. Give me another equation, another Maxwell's equation.
Maxwell's equation.
The first one, you said there are four Maxwell's equations, right?
Yeah. So divergence of magnetic field is 0, del dot B equal to 0.
Del dot B is equal to 0. Did we lose someone? Okay.
Yeah, Avi maybe his connection something.
Okay. that's equal to 0, right? And notice if and what's the name of this equation, by the way? The first one is called Gauss's law.
Second one, not Ampere. Ampere's law is another one.
Yeah, apparently there is no name for this.
Okay.
Apparently there is no name for this. If you can come up with name.
Okay.
Yeah. Abhi is back, I think. Abhiyan is.
Mine is problem.
Yeah, internet issues, I guess.
No, it's fine.
Okay. So two equations. This is, and what does the 0 mean? Just by looking at the two, you would think that, oh, that's a charge. That should be a magnetic something, magnetic charge, but it doesn't exist.
Yeah.
Right? So this is a statement that there is north and south pole of a magnet cannot be separated. Right? If you could separate it, that means that will come in here. Right? That's the magnetic charge, but we don't have it, so that's 0. What's the rest of the two equations? Actually, let me write this a little below. There are two more equations, right? This is no name, right? Two more equations, help me with that.
Yeah, the Ampere's law is, I think, the surface integral of magnetic field is equal to.
Yeah, that's the integral form. Good. Ampere's law.
Yeah.
Ampere's law.
And this is equal to mu0 I, current and the.
Yeah, Ampere's law tells that it's not surface integral, it's a line integral. Yeah. So this is dl, right? Dotted with the magnetic field.
Yeah.
Is equal to
mu0 I.
mu0 times I. That's okay. Is that correct? Is that correct? I say it's wrong. Or this is how we study it at an introductory level physics course, but there is a correction to this.
I mean, the closed loop is closed or something.
Oh yeah, that's a closed loop. Sorry, that's my mistake. I meant to write closed loop. Yeah, that's correct. But even then, this is not complete.
There's the additional term.
Yeah.
I forgot.
There's an additional term. Good.
Is there multiple of 2 pi? Is there multiple of 2 pi?
No. This is what Ampere did, correct? But then Maxwell said, this is where Maxwell's called. Why is Maxwell's name in this? This is actually Gauss. This was known. This is Ampere's, and the next one is Faraday's law, right? This is called Faraday. So where is Maxwell in here, right? Why are these equations called Maxwell equations? And Maxwell's contribution was this, but it was a very important contribution in the sense that connected all the 4 equations. So there is a new term in here, and he said that magnetic field can be created by current, but there is another way you can create a magnetic field. How is that? How do you create a magnetic field without a current?
Change in electric field.
Change.
Oh yeah, there's an induced magnetic field.
Very good, very good. So there is a change in electric field can create a magnetic field, and that comes out as dE
by dt.
So yeah, dB by dt, but then I need the flux, right? So this is d by dt of the flux of the electric field. Okay. It's not the electric field that comes in, it is the flux of the electric field that comes in. This is much easier seen in the differential form. There might be an epsilon or mu naught that I'm missing here. So let me put that in here and then I'll come back to that. So here, this is a divergence. Now we write curl of a magnetic field. Okay. And so this is the same Ampere's law I'm writing. This is, and that is R of T also. Let me not write it to save some space. And this is minus of d by dt of epsilon naught times electric field. Same thing, notice there is epsilon naught times E, there is an epsilon naught times E, and
Sorry to interrupt, Professor. Is it a minus sign or equal sign?
this is minus sign. Oh, it's not easily visible there, that's not good. This is minus sign. If I write it as equal, then I make it a plus. And that's equal to J, where J
Density.
is the current density. Good.
Correct.
This is the current density. To get the integral form, I integrate this on a surface, right? So if I were to integrate this on a surface, so that's dA, right? Dotted with del cross B minus of d by dt of epsilon naught times dA dotted with E, electric field on the same surface. So I'm integrating this, and that's equal to dA dotted with J. This doesn't have to be a closed surface, any surface, but if there is a surface and you're calculating the curl of something, then it is a line integral of the closed closed integral on the boundary of the surface. So let me call this as S. S and S, that's the surface. And this becomes a line integral where the curved line is the boundary of the surface, dotted with the magnetic field, minus of time derivative of epsilon naught times the flux of the electric field, that's the flux. And this is defined as a current, right? Current per unit area was the current density that we talked about. So this is the current, right? This seems to have a mu naught missing, so I should be careful here. Right? I think I messed up a little bit. There should be a mu naught here. So let me write this as H. So typically we say this is H, and B is equal to mu naught times H. Okay. So that's H, and that will bring in, so let me write this as B of H. But H is B over mu naught, and that's where that mu naught is hiding in this equation. Is that clear? If the flux of the electric field was zero, or not the flux, the rate at which the flux is changing in time, that's zero, then we have our Ampere's law in the usual form, the standard standard Ampere's law. So this is the integral form of Ampere's. Is that clear? Any questions there? Any questions? Okay. So we will again, as I said, we will use the differential form. Let's get rid of this. And H is B, so as well write this as H over mu naught, right? So that then I don't have to define this. Oh, did I? Oh, no, H, no, I just say B over mu naught. Right?
B over.
B over mu, yeah. Okay, so that's your 3 equation. What's the 4th equation? That's a Faraday's law. So what is Faraday's law? Either in integral or differential form.
Call of electric field equals del B by del T.
That's correct. Very good. Right. Here we say change in electric field can create a magnetic field. Here we say that you can create a curl in the electric field from a magnetic field, and there is a sign difference here plus dB by dt. And notice again, there is no, like we have an electric current here, there is no magnetic current. So if you had a magnetic charge, it can actually move around, and if it moves around, it will show up here. Like that's your 2 zeros have a very special place in the Maxwell's equation. That's your 4 Maxwell's equation. Again, notice on the right side, I write the charge and the movement of charges or the current associated with the charges. And what Maxwell's equation tells us is if there is a charge and a current, what is the electric and magnetic field? Right. So the content of Maxwell's equation again is electric and magnetic field, right? It is time dependent quantities. And actually no arrow on that side, only on this side, right? So that is rho of RT, and this is J. Okay. Give me the charges and currents, and Maxwell equation gives you a way to calculate what is the electric field and the magnetic field it will create. But that's an incomplete story in the sense that the moment you create electric and magnetic field, it will exert a force on these charges. It will disturb this, right? So then we should ask, what is that governed by? Who determines that? Like, what are the equations that tell us the connection between electric and magnetic field exerting a force on charges and currents? What is that equation? Maxwell's equation gives you this way. What's the other way?
Force.
Yeah, force, correct. What is that expression for that force? If you have a charge in a magnetic and electric field, what's the force experienced by the charge?
F equal to QE.
QE electric field, magnetic field.
Okay. So the
QEV.
force is the electric and magnetic fields is Q
QE
times electric field.
Electric field
plus
It should have time and position dependence plus Q times V
times V.
crossed with magnetic field. What is this equation called?
Lorentz.
Yeah, Lorentz force, right? We have the left-hand side equations in terms of charge density and current density, right? So it will be nice, and this right side is associated with only one charge, right? But in general, we have more than one charges. We have a density, so we would like to write the same thing on the right side also. That's very straightforward. You just divide this by volume. Divided by volume and divide this by volume. Whatever I do on one term, I have to do that for each term. This becomes force density now. It is dependent on position and time. Okay. So this is a small, tiny element of volume in space and time. And you can ask, what is the force acting on that volume, right? This is the force per unit volume, right? So we have to talk about a per unit volume of space, only if that is matter in there. The expectation is that it's matter is distributed around, right? That's equal. Charge per unit volume is rho. Times electric field, which could have all the position and time dependence. And what about this? We have charge times velocity divided by volume. That's exactly the current density. That's the definition of the current density. Okay, J charge multiplied by the velocity. Right? So this is J at that same space point R crossed with the magnetic field. So it's a vector equation. And here now we have, so given the electric field, how does it affect this? So, so again, how do we see this? There is electric and magnetic field. Let me write it like this. And this creating this, affecting this is by Maxwell equations. So that's rho and that's J. The other side, electric field exerting a force on a charge and current. This is by the Lorentz equation, Lorentz force. But Lorentz force is very classical in nature if you want. If you want a more sophisticated version of that, that's given by the Dirac equation. Or the Schrodinger equation, yeah. Lorentz force or a Schrodinger equation or a Dirac equation. And that's what is used to study if the electric and magnetic field is given, how does it affect this? But either one is not correct, right? Either one misses the point that when you're doing this way, you're not taking care of the fact that electric field, how does it disturb that? In principle, you have to keep these two things together. And that's what is called quantum electrodynamics. When you have both taken care of, that's called quantum electrodynamics. And broadly, it's called quantum field theory. So quantum field theory is the theory that does not neglect this one-sided effect and takes care of this whole thing together. We will not be doing that. Okay. What we will be doing is mostly the first part, Maxwell's equation. If we have charge and current, even if it is moving, it's okay. Under some approximations, we will be able to tell what is the electric and magnetic field, especially the radiation part, where when you're really far away, if the charges are happening, so if you have an electron inside your sample moving around and you're about 5 meters away from that sample, we are practically at infinity. So that's called a far field approximation. And in that approximation, you can get pretty precise results, very nice results. And that's what is called radiation. And that's what we will spend a good bit of time. But that's our Maxwell's equation we have. And now let's see what we are going to do now is for a moment, not worry about the Lorentz force equation, just the Maxwell's equation. What are the conclusions we can make out of Maxwell's equation? That's what we want to see. But before that, maybe I should point out that, let me go back to the Maxwell's equation. Right. In Maxwell's equation, if I remove the time dependence, right, I completely remove the time dependence, then this term goes away, right? And this term goes away. Correct? And of course, this time is no more there. We are saying that there is no time dependence. I don't have to write this t dependence in there, right? In that case, notice that first two equations only have electric field, and the next two equations only have magnetic field. That's magnetostatics. So this is electrostatics. And that's magnetostatics. Okay. Just by removing those two terms. So what are the equations governing electrostatics? It's good to write it down once again and see the analogy. So we have electrostatics, which says that the divergence of the electric field is equal to rho over epsilon naught. I move the epsilon naught to the right, and curl is 0. And if you see magnetostatics, it's very similar, but it's subtle. You have L dotted with B, which is 0. Like this is a curl-free concept. Electric field in the static situation does not have any curl, but has divergence, and magnetostatics has no divergence, but has curl. And this is mu naught times J. Right. Okay. Divergence means that, or let me say, curl free means that, a very naively speaking, electric field will never show these kind of properties. So electric field has electric field lines associated with it, right? So you will never see a point charge or an electric field at a point having this curl structure. Like think of a magnetic field. Magnetic field always comes in circles, right? Magnetic field never originate from a point and end in a point. They always go in circles around, right? So that's the idea of a something having a curve. Electric field will never show that behavior in electrostatics. If you go out of electrostatics, all that is possible, right? But because then the curl is not zero. In electrostatic, you usually have a positive charge where you create the electric field can be created in this form. It doesn't have to be radially outward, and that could be a negative charge where it goes in. So there's always a source of an electric field. There is a sink of an electric field. That's a positive charge, that's a negative charge. And the divergence is a measure of that source and sink. Okay. So that's something nice about it. If you have a curl of something to be equal to 0, it means that the electric field can be written in terms of an electric potential. Okay, so this implies, just because it is curl is 0, it implies that electric field can be written as gradient of a potential. Did you use phi in your courses or did you use V? Sometimes in elementary courses we use V.
I think in Viv's book it's V, but
V.
it's okay.
Okay.
Maybe V or phi.
Yeah, so we are going to use phi. That's a
Yeah.
small.
We use phi.
We used phi. Okay, great. Okay. Electric field is the negative gradient of a scalar potential only if electrostatics is true. Okay. If it was not electrostatics, there is one more term in here, which is dA by dt. We'll talk about that again, but we don't have any time dependence. This is not there. Okay. We will talk about that again in one of these lectures.
Professor, I have a question.
Yes, please.
Since you mentioned scalar potential, I forgot actually what's is scalar potential and what is vector potential.
Oh, okay. If I have a curl of something to be 0, let's go back to, let's see how we can promote this. Let's go to the idea of, so this is an independent discussion, but it's having a one-to-one connection, okay?
Mm-hmm.
So we define the work done by a force as, what's the work done by a force?
Force
Into
displacement or using integration, I think.
That displacement times the force, right? So it is
F dot ds or dl,
dl dotted with
Yes.
the force, correct? Okay.
Mm-hmm.
Which means that if I were to interpret this, I say I'm moving an object from point 1 to point 2, right? So this is, let's say, position R1. That's position R2. Correct? Since it's three-dimensional space, I can go from this R1 to R2. And if you notice, or let me define this. So this is along a path, and the dot product of this dl, so there is a tiny elements dl here, right? Dotted with whatever the force is acting on that point, right? That's your work done by the force. But where is the information about this path in this integral? Is the question clear?
Yeah, I mean only the initial point and final point. That's the only information.
Yeah, but so what if I'm going from the initial point to the final point using this path? So in principle, the work done, if you carefully read in the definitions, there is a path dependence in it.
Yeah.
You have to specify the path. Otherwise, the work done is not very well defined. But, okay, now there is a but here, and that's the point that is it possible that there are some forces which do not depend on this path?
Conservative force.
Very good, conservative forces, correct?
Yeah.
Let's say that this force is conservative. Then I do not have to talk about a path.
Path, yeah, only the initial and final point.
Okay, it's only the initial and the final path. And if it is independent of the path, I can go this direction and then I come back in this direction, and then what will happen? It will be zero, right?
Yeah, total will be 0.
So if it is a conservative force, I have this interesting fact for a closed path, the L dotted with F is equal to 0. Correct?
Yes.
If the closed integral of a vector field dotted with dl is 0, what can you conclude?
Force is 0.
No,
No.
force is 0.
Conservative.
What is Stokes' theorem?
Stokes theorem, yeah, it can be expressed as a negativity and of a potential.
No, as that is there. We are coming to that. What we are saying is that this means that
Surface.
using, yeah, we can do this on a surface, dA
dA.
dotted with del cross F is equal to 0. Right?
Yeah.
But if a surface integral, now in this case, if something is 0, you cannot say force is 0 because it's only on the boundary. Here, if this is equal to 0, since it's on the complete surface, then you say that del cross F is 0. The curl of the force is equal to 0. Okay. So what happened? Work done is not 0 in general. It's not path independent in general. So first point is path independence, right? That's what we used, path independence. Not all forces are path independent. Okay, there are very special forces that are path independent. There are very few conservative forces. One is gravity, one is electrostatics, and then there is a spring force. And there is, of course, standard model has all these forces, fundamental forces. Only the fundamental forces are conservative. Not all forces are conservative. Okay. So path independence implies del cross F is equal to 0. But path independence also tells us that when I'm going from this point to that point, I don't have to care about the path. So it seems to suggest that at every point there is a special property. Right? Force is the change in something. And that leads to the idea of energy. In fact, it's called the potential energy. If the curl of something is equal to 0, that particular force can be written as the negative gradient of something. What is this something?
Potential.
Potential energy. Use the potential energy there, right? Not every force has a potential energy associated with it. You talk about gravitational potential energy. You talk about electrostatic potential energy. You never talk about the potential energy associated with friction, for example, right? You don't talk about the potential energy associated with the normal force. That doesn't exist. It's only very special forces that's there. So notice again what happened, path independence. Importantly, the curl of something is zero, implied that there is an energy, right? Now there is a very similar thing here. Curl of the electric field is zero, correct? I can do the whole game with this again. Start from here, go back, trace back my steps, and I learned that the line integral of the electric field in a closed path is zero. The same idea, there has to be a scalar field, scalar because this is a scalar quantity, energy is a scalar quantity. Exactly like energy, in this case you call energy per unit charge, and that's the electric potential. Is that clear?
Yeah.
Did I answer your question?
Yeah.
Why? Yeah. Okay. So all
Thank
this.
you, brother.
Yeah, good question. So that's your electric field being negative gradient of phi. Okay. So this implies this. Okay.
Yeah.
If that is the case, if this is the same as this, I go back to this equation. I substitute electric field as gradient of phi, and I get an equation, negative gradient dotted with gradient is called the Laplacian.
Laplacian.
Right? Laplacian of the scalar potential is equal to rho. Let me just say rho over epsilon naught. Okay. Again, what are we talking about? Give me a charge distribution. I will give you the electric potential. If I know the electric potential, I can take the gradient and I can know the electric field. Right? The same idea. Give me the charge. What is the electric field? That's the question we are talking about. There is one special situation, special case, and that is when the charge is a point charge. Okay. When it is a point, what is the electric charge distribution or the electric charge density when there is only one charge in the universe? What is rho?
Zero.
No, there is a point charge. If it is zero, then it is like vacuum, right? There is one point charge.
I mean, 1 point charge.
Right, so we have
Charge
single
divided
point
by the
charge.
small volume.
Yeah.
The limit of the volume goes to zero.
So rho of R is equal to, so it is positioned at the so let's say R naught, at position R naught, right? That's the position of the charge. So charge density is zero if R
Oh yeah, you're
is
talking
not
about
equal to R naught,
direct delta function.
right? And it is, yeah, you said delta function, that's correct. And it is equal to something if R is equal to R naught. Correct?
Mm-hmm.
But there is also one more conditions to be obeyed, and that is that if I were to integrate over all space,
It should be 1.
it should be charge Q, right? Charge density integrated should be charge Q. Good. right? So d cube r of rho of r should be equal to q, right? That's a point charge. That's a definition of point charge. The density integrated over all volume should give me my rho. And then you suddenly scratch your head and ask, what function is that? This is 0 everywhere. And this better be infinity if I have to get a q out of it, or I have to get a 1 out of it, right?
Yeah.
So this has to be infinity, right? So that's a very weird function, right? But that's called the delta function, okay? Exactly that interpretation that it is 0 everywhere, except at one point, which is probably infinity. It is not probably, it is. It has to be infinity, but it's a very special infinity in the sense that this infinity, when you make the 0 multiplied by that infinity, exactly cancels out. Very small, very big, cancels out to give you this q. Okay, so what is the charge density then? For a point charge, I don't have to write all this specialty. It's called the delta function, and it is q times delta function. I say 3 because it has 3 delta functions, one in x, one in y, one in z, and this is r minus r naught. Is that clear? Like at least qualitatively clear, delta function. Have you guys worked with delta functions sufficiently?
Yeah, in the first semester we did some maths related to delta function.
Okay, yeah, we will see a lot of it. Okay. What is the dimension of delta function?
Dimension.
Is that clear, my question? So the delta of x, dimension, that's what we say, right? Dimension of delta of x. What is that equal to? Do you measure it in kgs? You measure it in charge?
Is length?
Length, good. Want to try again? Yeah, length, maybe.
Volume?
Volume, very good, but help me a little bit. If this was volume, right? This is charge density.
Oh. Charge density, Qy.
Charge per unit volume. I mean charge density.
Yeah, this is charge per unit volume. So what can you say about the delta function? It has
Per
to be
unit volume. Per unit
per
volume.
unit volume, right? Very
Yeah.
good. Right. So this is 3 delta functions. So if you have a 1 delta function, it is just the dimension of x. It doesn't really have to be volume or length. Whatever is the dimension of x. X could be time, for example, or it could be kg. Whatever is the dimension of x, it is inverse of that. In our case, it is the position. So it is the inverse of the position, which makes sense that you're saying that charge per unit volume delta function is really tiny. That tiny piece of volume is what we are talking about. Okay. Okay, great. So if that's the charge per unit volume, let me talk about what is the electric potential due to a point charge. Okay. So I say that on the right hand side, I want to put Q over epsilon naught and delta function. Can I take a few more minutes? It's 1:50.
Yeah,
Yes, sure.
Right? Okay. This is called Laplacian. Okay. Now, what is, so this, whatever is your phi, is no more the same phi, it is a very special phi. Correct? This is the electric potential due to a point charge. Correct?
Yeah.
This is the electric potential due to a point charge. Let me play some gimmick here. I multiply this by epsilon naught and divide it by q and get rid of the right hand side. Right? This quantity, you remove it and rename this, and let's say this is G. Okay, that's called the Green's function. Okay, so Green's function is not a magic at all. It is the electric potential due to a point charge. That's it, simple. Okay, what is the electric potential due to a point charge?
Green function.
Yeah, that's a definition, but this is a point charge, right? Go to elementary physics. What is the expression for an electric potential due to a point charge?
1 by 4 pi E0 Q by R.
Very good, right? 1 over 4 pi epsilon naught
Q by R.
Q by R, right? But remember that I had multiplied by an epsilon naught and divided by a Q. So I had to remove that. Remove the Q, remove the epsilon naught. What is left is 4 pi R. And it's not really R, it is R minus R naught. That's the Green's function, that's it. I don't have to solve it, I know the Green's function because that's a definition of the Green's function. Okay, but of course, there are standard procedure you can follow to actually calculate the Green's function mathematically, but conceptually, that's what Green's function is the electric potential due to a point charge. You did this last semester. What we will do here is that we are going to make this move. I want to remove this constraint, right? This was 0, this is not 0. Right? This is statics. We don't want to work in statics. We want to bring in the time dependence and then ask the question, if a point charge is moving, what is the Green's function? And once I know the Green's function, I just have to integrate it, I get the electric field. That will be the logic we will follow, right? Get the one point charge, integrate it, you get everything. Okay, so Green's function is going to play a central role in the sense that if I know 1 point charge, then the superposition principle tells me that I just have to integrate this. Okay. Do you really don't have any class after this? Hriday, Ken?
Yeah, we have class after, but it's late, quite late. So
It's at 4.
It's at 4.
Yeah, I have a class after this actually. So
Okay, right at 3 o'clock? Sorry, 2 o'clock?
yeah, right at 2.
Okay, so then I should stop here. Otherwise, I would have done the same thing for magnetostatics. We'll come back and do that. So let's go slow. So no problem. Okay. 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 Thank you. And see you guys on Thursday and hopefully in person on the next Tuesday.
yeah, hopefully.
Okay.
Thank you, Professor.
Okay. Take care. Enjoy, guys. Yeah. Nice seeing you back. Yeah.
And I see you too.
Except Hriday, I couldn't see you.
Oh, sorry. I'll definitely change it next time.
Yeah. No.
I don't know
no
what happens to
problem.
my camera.
Yeah. I was just saying. Don't worry. Good. Okay, Abhiyan.